Today we're going to be looking at motion, forces and energy. So if you've been looking at the study of motion and how forces interact with a moving object, that naturally leads us on to the concept of energy. Now, energy is something that we come across every day. We talk about, we use the term energy every day. But if you were to ask a physicist to actually define what energy means, that would be something that would be a far more complex matter. We know there's many forms of energy. And these forms can be changed from one form to another. For example, electrical energy can be, when you put it through a light bulb, is transformed into light and also some heat, which are also forms of energy. One of the most influential physicists of the 20th century was a Nobel Prize winning physicist called Richard Feynman. And when he was asked, what is energy? This is what Feynman said. Now, just for as a side note, if you were to when you come to the study of quantum physics later on, Feynman's lecture notes on quantum physics are excellent resource to have. Anyway, this is how Feynman described what energy is. There is a fact, or if you wish, a law governing all natural phenomena. That is known to date. There is no known exception to this law. It is exact so far as we know. The law is called the conservation of energy. He goes on to say, it states that there is a certain quantity which we call energy that does not change in the manifold changes that nature undergoes. That is the most abstract idea because it is a mathematical principle. It says it's a numerical quantity which does not change when something happens. It is not a description of a mechanism or anything concrete. It is a strange fact that when we calculate some number and when we finish watching nature go through her tricks and calculate the number again, it is the same. It is important to realise that in physics today we have no knowledge of what energy is. It is not that way. It is an abstract thing in that it does not tell us the mechanism or the reason for such various formulas. So that was Richard Feynman's way of explaining what energy is. And go ahead and try and explain to yourself what energy is. It's just a term we use all the time, but to actually explain what it is a completely different thing. But there is a certain quantity of energy in the universe, and it is always conserved. Energy can be changed from one thing to another. It can also be changed into mass. Einstein had his famous formula, E = mc squared, where c is the speed of light. So energy and mass are two interchangeable things. If you take all the mass of something, you can change it into pure energy, and energy can be changed into mass. But this is a finite quantity in the universe, and as such we use the conservation of energy law to help us with our calculations and understanding how different systems work. So let's look at this in a not such an abstract way. Let's look at let's consider objects falling under gravity. So let's consider we've got some ball up here, and it's going to fall down a height of 3 meters, and our ball has a mass of 2 kilograms, and it's going to fall up here. We say it's got gravitational potential energy, and the symbol for that is EP, gravitational potential energy. It's going to fall down here. It's at height 0. It's got no gravitational potential energy. Gravity's still acting on it, but it's not moving any further because the ground is here. All this energy is going to get converted into kinetic energy when it comes down to here. So up here it's not moving until we release it, so it's got 0 kinetic energy, and it's going to accelerate, and so all this gravitational potential energy gets converted into kinetic energy. So we can work out the gravitational potential energy with the formula mass times g, which is gravitational field strength, times the height, and we use 9.8 as our value for g, and we slot this in. It's 2 times 9.8 times the height, which is 3, and that gives us a gravitational potential energy of 58.8 joules. Kinetic energy is, we'll call it EK, is half mv squared, and that is going to equal 58.8 joules once it falls just before it lands on the ground. And we can use this to calculate our velocity. So that's going to be equal to half times the mass, which was 2, times v squared. So v is going to be 5.7 meters per second. Let's look at another example. A mass, that's a terrible M, of 4 kilograms is released from a height of 2.4 meters. It falls and rebounds to 1.8 meters. So we've got our ball, it falls down to here, and that is 2.4 meters from the height it falls, and then it bounces back up to a height of 1.8 meters. So we want to calculate the potential energy at each height and we want to calculate the kinetic energy when, firstly, just as it makes contact with the ground down here, and secondly, after it leaves the ground. So the first one is our gravitational potential energy at the beginning is mgh. It is, what's the mass? 4 times 9.8 times 2.4, and we work that out to get 94 joules. So that is the initial potential energy. Then after it rebounds, we've got mgh again, which is still 4, still 9.8 times 1.8, and that gives us 71 joules. So that's after rebound. Now, the as it makes contact, so as it lands, so as it just comes down here, the kinetic energy is going to be equal to the initial, we'll call it initial, gravitational potential energy. So all this potential energy is going to be converted into kinetic energy. So that is 94, so that is going to be equal to half mv squared. And so we can use that to then calculate the maximum downwards velocity of 6.9 meters per second. Now, as it rebounds, it doesn't rebound to the same height. So, but the kinetic energy when it leaves the ground is going to be all converted into gravitational potential energy. So we use the gravitation, so the kinetic energy rebound is going to be equal to the gravitational potential energy rebound, which is 71, which will be equal to half mv, the velocity on the rebound, squared. And we work that out as 5.9 meters per second. So the velocity after it bounces back is going to be less. And the reason it doesn't, we've already said that the law of conservation of energy says that energy can't be lost, that the energy at the beginning in this system is the same as it was in the beginning. However, it doesn't, if that would suggest that it should rebound up to the same height as it had at the beginning. But it doesn't. We've got some missing energy. There's an amount of energy appears lost, but it's not missing. Some energy is transformed into sound. So when you hear it bounce on the ground, that's some of that gravitational potential energy that was converted into kinetic energy is now being transformed into sound. And heat via friction. So when it hits the ground, there's a frictional force which will see some of the energy transformed into heat, and then it bounces. So then when it rebounds, the kinetic energy at the rebound is going to be less than what the kinetic energy was just as it hit the ground, because you've got an energy transfer happening here. So it's not being lost, it's been transformed into other forms of energy. There is also going to be the initial energy is also gradually going to be lost through heat and sound, and lost to friction as this ball travels through the air. So even when we think about this ball, if we just think about the ball here bouncing down, the fact is that not all the energy, the gravitational potential energy, is actually going to be transformed into kinetic energy. Throughout this whole motion, energy is being lost through friction as the ball travels through the air, and that'll be in the form of heat. So energy is conserved, but you may not measure all the parts of the energy as you observe the moving parts because of this loss of energy by predominantly friction. So let's think about some motion through down slopes. So let's think about a boy in a sledge. And he's moving down. The boy and sled have a mass of 55 kilograms, a combined mass. Now when you're calculating the gravitational potential energy, it's the height here, and it's 22 meters. It's not the distance that you would go down the slope, it's the actual height. So we can calculate his gravitational potential energy, mgh, is 55 times 9.8 times 22, which is 11,858 joules. And we're just going to call that 12,000 joules, round that up. If his velocity at the bottom of the slope is 14.2 meters per second, then his kinetic energy at the bottom is going to be, with half mv squared, is going to be a half times 55 times 14.2, and that's squared. That comes out at 5,500. We're going to round it up to make the numbers nicer to deal with. 5,500 joules. There's a huge difference between 12,000 and 5,500. So there's a large difference in the gravitational potential and kinetic energy. We know that the energy can't be missed and it can't be lost, so it has been transferred into another height and into another type. Energy has been converted to heat, mainly due to friction. So we could describe this in 3 different ways, and it's good to kind of be comfortable using the terminology. So, for example, if you had this kind of question in the exam, being able to explain what energy transformations are occurring and be able to use the correct terminology is really important. So we could say either energy has been used to overcome friction, or we could say work has been done to overcome friction, and this results in a transfer of energy. Or you could say simply energy has been lost to heat. I think the second one is the strongest explanation, because it brings in the whole concept of work being done to overcome friction. It uses that term, work done. The term work done is used widely in these types of problems. And as the boy slides down this hill, there's friction between the boy and the snow. And so to be able to move in this direction, he's having to overcome the friction. There's friction in that direction, and he's got the downward force due to gravity in this direction that's pushing him down the slope. Because the weight, the component of weight down the slope is greater than the frictional force up the slope, he accelerates down the hill. But this system of the boy in his sled there has to be work done against the friction for him to be moving down the slope. So that energy is used, or is transferred to overcome this frictional force. So we can look at this situation and we can say the work done is going to be the initial initial energy, which was 11,858 minus, and I'll use the proper number, not the rounded one, 5,545 joules, and that gives us 6,313 joules of work done in overcoming friction. Now we know that work done is equal to the force times displacement. Let's say that this slope here is 60, oops a daisy, oh that's terrible, 65 metres. We can then work out the force. So the force would be this 6,313 divided by the 65, which gives us 97.1 newtons of friction acting against the force. Let's do one more example. This time we're going to do not on a slope, on a flat, but another problem involving friction. So a truck of 3,000 kilograms travels along the motorway at 24 meters per second. The driver sees a warning light come on and brakes until the truck stops. Calculate the kinetic energy of the truck initially. So we've got the kinetic energy is half mv squared, so it's a half times 3,000 times 24 squared, and that's going to give us 864,000 joules. The truck stops in 72 meters. Calculate the force of friction. So let's think about our truck. I'm just going to do a box for our truck. It had a velocity of 24 meters per second and its mass is 3,000 kilograms. And so up here, this is where it starts, and then it stops here and its velocity is 0. So here, all the kinetic energy here is our 864,000 joules, but here it's got 0 kinetic energy. What's happened to the energy? It's not on a slope, so we've not got gravitational potential energy. All that energy is being converted into work done by friction. So the work done is going to be 864,000 joules, and that's the frictional force times the distance, and we're told the distance is 72 meters. So the frictional force will be 864,000 divided by 72, which is 12,000 12,000 newtons. So that this 864,000 joules is going to be, when the brakes are applied, we've got a frictional force of 12,000 newtons, and all that kinetic energy is going to be changed into heat and transferred into heat and sound in the tyres. And that heat and sound is going to be in the braking system, but also on the tarmac on the road. So I hope that makes sense.